In this video, we're going to talk more about free energy and equilibrium constants and try to look at the relationship between the two. So we have developed this relationship described by the equation that standard free energy is going to be equal to the negative R temperature times the natural log of our equilibrium constant K. And so this is going to allow us to imply some general relationships about free energy and equilibrium constant. If we know an equilibrium constant value, we use it to predict if a reaction to equilibrium will favor our products or our reactants. Will we form lots of a product or very little of a product? And we use that to understand concepts like weak and strong acids and bases, for an example. So here we've got a table that kind of shows the relationship between if K is doing this, here's what the change in standard free energy is doing. So when K is very large, it's bigger than 1, we say that equilibrium is going to favor our products, that we'll have more of them once we actually reach equilibrium. If we were trying to make something and we wanted to make a lot of it, we would want to choose reactions that got us there that had large K values because we would be favoring products and it'd be easier to extract more of that product out of a reaction. So when our K value is larger than 1, we're going to see using this equation that our standard free energy is going to be less than 1. So a negative change in standard free energy is going to correspond to a large change in our products. Or sorry, a large will correspond to more products at equilibrium. Sorry about that. So then the opposite of this, when our equilibrium constant is less than 1, we expect to have more reactants at equilibrium. So an example of this would be the weak acid. So in this case, if we were trying to evaluate if we had more products or reactants at equilibrium and we only knew standard free energy change, we would be looking for a positive change in standard free energy to predict that more reactants would be abundant at equilibrium. Now, in the case where we're at at 1 for K, that's when everything is equal. We have roughly equal amounts of products and reactants when we actually hit equilibrium. And if K is 1, then that means our standard free energy change is actually going to be 0. So we can use these general values of our free energy to evaluate what the reaction looks like at equilibrium. Let's look at this graphically. So these 3 different graphs are looking at free energy as a reaction progresses, or the extent of a reaction, where we have either all of our reactants or all products. And we're going to try to look a little bit more at this relationship between K and free energy. And so this line up here, and when thinking about free energy, we're really thinking about this difference right here. So if looking at this difference right here is going to correspond to my change in energy, free energy right here. And I'm looking at the free energy of my products and the free energy of my reactants here. And so same thing right here. Here we've got our free energy of our reactants, and here's our free energy of our products. And again, so looking at this change in delta G here on our first one, we're looking at K is less than 1. So in this situation, we expect our change in free energy to be positive. And we have right here, if we're looking at our products minus our reactants, we have that positive free energy right here. We're increasing the amount of free energy if we went all the way from all reactants to all products. And so we're corresponding that change in free energy that's going to be positive to that K less than 1. So we see that relationship that the sign of our change in free energy is opposite that of our K for less than 1 or more than 1, which isn't really negative or positive because 1's the 0 rather than 0. So looking at this, we can see that our graph is showing a minimum that's going to favor more of A than B. And so this local minima is coming in a place in our extent of our reaction where we have more reactants than we have products. And so this right here, this is when we are at equilibrium. It's when we've reached K for the reaction. And so we're minimizing the amount of free energy when we're at equilibrium. And so this is a driving force to have our balance of reactants versus products favor our reactants. And you can see the opposite of it on the graph to the right. So in this case, our reactants free energy is larger than our products free energy. And so we have a negative value for that change in free energy between A, our reactants, and B, our products. And we also see, so this is for K larger than 1, so we expect to favor products. So when we have this difference where we have a negative change in energy between reactants and products, we see that graph shape change, so that way our local minimum is now at a point in the extent of the reaction where we have more products than we have reactants. And so when we reach equilibrium, when we hit K, we're going to have more products than we do reactants because of that difference in our free energy when we compare those reactants and products. Now, if our change in free energy is 0, that means we would have the same number of our reactants and products. And that's our bottom graph right here. So here our change in energy, free energy is 0. And so they're equal. And when those are equal, we're going to see that local minimum come right in between the two on our reaction, our extent of our reaction, and we're going to see equal amounts of our products and our reactants. And so that difference in free energy between reactants and products, which is characterized by that change in standard free energy, really changes this graph and creates that driving force towards products or towards reactants.